Now we've learned all of our derivative rules, we've seen applications, we've seen optimization, we've seen related rates, we found maximums and minimums, equations of tangent lines. We understand how the limit applies to the derivative, that the limit is actually the foundation of a derivative, that every time you're doing a derivative, you are actually evaluating a limit, and that is finding the slope of the tangent line to a function anywhere on that function. Now we're going to get to other functions that we haven't talked about yet, but that I have been talking about for a while and telling you how important and fun they are. Specifically, we're going to get to the exponential function today, then we'll get to logs and then trig, but we want to talk about the exponential function. And to start that, we're going to always start with e to the x. So we want to think about, well, where does e come from? What is e? Well, there are many ways in which we can develop the constant e. We have talked about these back in first semester in Unit 6 when we had our exponential and log unit. Two of those ways that I showed you back then, even though we didn't know what a limit was at the time, was that if I take this expression 1 plus 1 over h raised to the h power, and I plug in values of h that get larger and larger and larger, so I do the limit as h goes to infinity, this expression will approach the constant e. And when we say that, that means it'll become the constant e as h goes to infinity. Another way in which we can manipulate this is if I take the expression 1 plus h to the 1 over h, and I plug in smaller and smaller and smaller values of h, then this expression will approach the constant e. So these are two different limits that are very similar, actually, more similar than you might think, that will help us find the value or the constant e. This is the idea we're going to use to find the derivative of the function e to the x. I am circling this continuously because, one, it's kind of fun, but two, this is the one that we are going to use to help us understand the derivative of e to the x. Why are we going to use this? Well, this one has the limit as h goes to 0, and what is our limit definition of the derivative? It's when h goes to 0. Very good. So what is the derivative of e to the x? If I think about it, if I asked you what's the derivative of e, that would be a trick question because e is a constant, so the derivative would be 0. E to the x is a function, and we need to know the derivative of e to the x. That's going to be the basis of every single exponential derivative. Okay, so the next thing that's going to happen is a little magic because it's really important that you understand what the derivative of e to the x is, but it's not something that I'm going to ask you to be able to come up with necessarily on your own. So I'm just going to show you the process and skip writing it down in front of you. So I want you to count to 3. 1, 2, 3. Boom. That was a pause for dramatic effect because I know your mind is blown, but you just wait. Just wait. This is going to get great. So if I have the function e to the x, f of x equals e to the x, I use my limit definition. I know that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So substitute in the function. That's the limit as h goes to 0 of e to the x plus h minus e to the x over h. Everyone with me? Keep up. Good. Moving on. The limit as h goes to 0 of e to the x times e to the h minus e to the x over h. What did I do? I used properties of exponents to split this term up into e to the x times e to the h. Keep moving. Nice. Limit as h goes to 0 of e to the x times the quantity e to the h minus 1 over h. What happened there? I factored out e to the x. Now, this is where that limit from the previous page comes in. So I know that e equals the limit as h goes to 0 of 1 plus h to the 1 over h. Well, this equals e as h goes to 0, right? So what if I raise both sides to the h? Then I end up with e to the h is 1 plus h. And remember, this is true when h gets infinitely small. So when I evaluate the limit as h goes to 0, e to the h as h goes to 0 will become approximately 1 plus h. That should also make sense because anything raised to the 0 power is 1, right? So e to the h as h becomes infinitely close to 0 should become infinitely close to 1 plus h. Okay, so now I'm going to substitute this into my limit here. So where I had e to the h, I'm going to make that 1 plus h. But then look what happens. The 1's cancel. Uh-oh. Do you see what's coming? Do you see it? Well, you probably do because it's on the screen. But then I have the limit as h goes to 0 of e to the x times h over h. I can reduce the h's. And now I can evaluate the limit, and I'm really just left with the limit as h goes to 0 of e to the x. So that has to equal e to the x. Again, that was a dramatic pause because I don't even know what's after mind blown. It's just mind more blown. But what we just found out was that the derivative of e to the x is e to the x. Think about what that means. That means that the rate of change of the function e to the x is always equivalent to the height of the function e to the x at any given x value. E to the x is the only function that has that property. Yes, with the exception of like the line y equals 0 where the height is 0 and the rate of change is 0. But still, e to the x, come on. I mean, that's amazing. Why do you think there are so many famous e's? Or people that have e to spell their name? Why do you think Eminem spells his name with an E as opposed to the traditional letter M ampersand M? Because E is awesome. Oh, sorry. So anyway, we know now, you need to know this, memorize it, love it, cherish it. The derivative of e to the x is e to the x. Well, what if it's not just x, right? What if it's some other exponential function in terms of x? So then the derivative d dx of e to the u, where again, u is just some function of x, would be e to the u du dx. So let's look at that. So if we want to find the derivative of f of x equals e to the 3x squared minus 2x, f prime of x is going to be e to the 3x squared minus 2x times the derivative of 3x squared minus 2x, which is going to be 6x minus 2. That's it. What about f of x equals e to the negative 3 over x? Let's try this one. Prime of x equals e to the negative 3 over x times, remember, do not do the quotient rule here, please. Do not do the quotient rule here. 3 over x squared. Sorry, that looks like a negative. It's not. And if we wanted to, you don't have to, but we could rewrite this as f prime of x equals 3e to the negative 3 over x squared. So either the purple or the red would be acceptable. Okay, now it's time to practice. So I want you to find any relative extrema of the function f of x equals x e to the x. Pause the video, unpause when you're ready to check. All right, hopefully you got that there is a relative minimum at -1 comma -1 over e. How do we come up with that? Great question. Product rule. So f prime of x is e to the x plus x e to the x, because what did we do? I did the derivative of the first times the second plus the first times the derivative of the second. Now we need to find our critical values, set it equal to 0. I factored out e to the x, set each factor equal to 0. E to the x can never equal 0. That's silly. There's a horizontal asymptote there. And then I get x equals -1 as a critical value. So I did my first derivative test, increasing, decreasing chart, plugged in -2, plugged in 0, plugging those into the first derivative, don't forget. I see negative, then I see positive, so use my derivative speak. Since f prime of x is less than 0 on negative infinity to -1, and f prime of x is greater than 0 on -1 to infinity, at x equals -1 is a relative min. But then I wanted to find the point, so f of -1 is -1 e to the -1, which is -1 over e, so the relative min is -1 comma -1 over e. Fantastic. We'll assume from your silence that right now there are no questions, but please speak up. Next one, I want you to try and find any inflection points. Yeah, second derivative. Pause the video. Unpause when you're ready to check. All right, here we found 2 points of inflection. One point is at 1 comma e to the negative 1/2. Another point is at negative 1 comma e to the negative 1/2. How do we come up with that? Good question. Take the derivative. F prime of x is e to the negative x squared over 2 times negative x. Now take the second derivative. Don't forget the product rule. So I do the derivative of the first, so e to the negative x squared over 2 times negative x times the second term, plus the first term, e to the negative x squared over 2 times the derivative of the second term, negative 1. Simplify a little bit, combine like terms. Negative x times negative x is positive x squared. This becomes just negative e to the negative x squared over 2. Factor out an e to the negative x squared over 2. Set the derivative equal to 0. E to the negative x squared over 2 can never equal 0. I get x squared minus 1 equals 0, x equals 1, x equals negative 1. Those are my possible points of inflection. Find or make my concavity chart. So negative 2, 0, positive 2. I get plus, minus, plus. So I see that I have 2 inflection points. Use my derivative speak since f double prime of x is greater than 0 on negative infinity, negative 1, and f double prime of x is less than 0 on negative 1 to 1 at x equals negative 1 is an inflection point. And since f double prime of x is less than 0 on negative 1 to 1, and f prime double prime of x is greater than 0 on 1 to infinity at x equals 1 is an inflection point, plug those values back into the original function to find the y values and get your inflection points. All right, last one. So find the equation of the tangent line to the curve at 0, 1. Y equals e to the x over x plus e to the x. That's a doozy. All right, have fun with that. Pause the video. Unpause when you're ready to check. All right, so we should end up with the equation y equals negative x plus 1 as the equation to the tangent line. The equation of the tangent line to the curve at the point 0, 1. How do we come up with that? Find the derivative. Have to do the quotient rule here. So bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I would not try to simplify this. I mean, you could if you want. No point though, because all we're going to do is plug in 0 for x, remember? Because we're trying to find the slope when x equals 0. So if I plug in 0 for x, I end up with negative 1. And then I already know the point is 0, 1. So conveniently, that is my y-intercept. So I can write this in either point slope or slope-intercept form. So I get y equals negative x plus 1. Any questions? All right, good lesson. So what we need to know the derivative of e to the x is e to the x, and the derivative of e to the u with respect to x is e to the u times du dx. You want to memorize this, okay? You don't want to have to come up with it every time. Also, real quick, going back to this one, keep in mind this is the type of problem we could also use a calculator on. I didn't emphasize that when we did this problem because I wanted you to practice doing the derivative with ease. However, this is definitely a calculator type problem if you were allowed to use a calculator. Back here, next thing I want you to think about also is, what if the base is not e, right? Like, what if it's 2? Then what would you do? Maybe give up, but maybe persevere, right? Yeah. Yeah, think about that while you sleep. All right. See you tomorrow.